Okay, welcome back, everyone. Let's continue our discussion of Bloch's theorem. So at the end of the last mini lecture, we were talking about the volume in K-space for each allowed value of the wave vector little k. And we came away with an interesting fact, which was that the volume of the reciprocal lattice primitive cell is equal to the total number of sites in a crystal. Again, this, as I mentioned before, foreshadows one of the important themes of the course, which is that the first Brillouin zone, the primitive cell of the reciprocal lattice, contains essentially all of the information about the crystal. Although this seems strange, this is actually not so different from what we found out in the Sommerfeld model. So let's just briefly connect those two. So if the volume of the real space primitive cell is little v, then the volume of the reciprocal lattice primitive cell is 2 pi cubed over v. over little v, or of course, little v is equal to big V over n. We can make the following statements. So we know that delta k is equal to b1 dot b2 cross b3 over capital N. So the volume in K-space per allowed value is the volume of the reciprocal lattice primitive cell divided by capital N. Well, this is equal to 2 pi cubed over little v times big N. But little v times big N is the same as big V. So the volume per point in K-space is 2 pi cubed over the total volume V, just like it was in the Sommerfeld model. So let's give another proof of Bloch's theorem. So you'll recall that the proof we gave in the last lecture relied on some formal arguments associated with translation operators. This next proof will rely on a Fourier expansion of both the potential and the wave function. We'll get the same result. They highlight different aspects of Bloch's theorem. Remember what it is that we're trying to prove. We know that the wave function of the Hamiltonian with the periodic potential is equal to a plane wave times some function with the periodicity of the lattice. Alternatively, we can express Bloch's theorem in the following way. If we displace the wave function by a Bouvet lattice vector big R, the result is e to the I k dot big R times psi at R. All right, so let's move ahead with the second proof. Implicitly in this proof, we will assume that we're using periodic boundary conditions, Born-von Karman boundary conditions. We'll expect that we can therefore expand the wave function in terms of plane waves in a Fourier expansion. So we'll say that we can write now the as yet unspecified wave function, the eigenfunction of the Hamiltonian that we're trying to find, in the following way. We can write it as a sum over wave vectors q of coefficients times plane waves. So this is the Fourier expansion of the wave function. Q satisfies our boundary condition. We'll also assume that we can write the potential as a similar Fourier expansion. Here, we're expanding it in reciprocal lattice vectors. This is the natural basis because these are the wave vectors that give plane waves with the periodicity of the lattice. Here, the Fourier coefficient u of k is equal to the integral of minus I k dot r times the potential u of r, where the integral goes over the real space primitive cell and where we've normalized by the volume of that primitive cell. So we're going to use these two facts, the fact that the potential itself is periodic, and therefore we can express it as a Fourier series, as well as the fact that the wave function can also be expressed in a Fourier series because we are using periodic boundary conditions to derive Bloch's theorem. So let's substitute these expressions into the Schrodinger equation. Remember, the energy operator, the kinetic energy operator is p squared over 2m. That's minus h bar squared over 2m times del squared acting on psi. Let's insert our expression for the wave function here. So two derivatives on psi brings down a factor of q squared. So the kinetic energy term will look like the sum on q times h bar squared over 2m times q squared, cq, the Fourier coefficient, times e to the I q dot r. Now we also need the product of the potential and the wave function. Again, using the expansions we wrote down before. Here's the potential. And the wave function. Let me just combine these two sums into one and write it as the sum over big K and little q, u, big K, c, q, e to the I, big K plus q dot r. Okay, now we're going to kind of massage these sums and be clever with our indexing to get this into a little bit of a nicer form. So let's set little q prime is equal to big K plus little q. This will allow us to write the product of u and psi as the sum over k and q prime, u k, c, q prime minus k, e to the I, q prime dot r. So if you like, I've just changed the origin of the sum over q here to make this expression a bit nicer. Okay, why stop at one relabeling? So let's set k as k prime, and let's set q prime as q. So we're just going to trade primes here. I'll leave that step to your imagination. And when we combine that with our expression for the kinetic energy, the Schrodinger equation gives the sum on q of e to the I q dot r times h bar squared over 2m times q squared. Here's the eigenvalue e that we're trying to find, times the Fourier coefficient of the wave function cq, plus the sum on k prime u k prime c of q minus k prime the whole equals 0. So this is the equation that we are solving, the Schrodinger equation. Again, here's the eigenvalue, the energy eigenvalue, and the wave function now is expressed in terms of these Fourier coefficients CQ, which correspond to the amplitudes of the plane wave at wave vector Q. Okay, so this whole sum must be equal to 0. Because the plane waves are orthogonal, it must be true that each term in this sum is also 0. So we can say that h bar squared over 2m q squared minus e times cq plus the sum on k prime u k prime c q minus k prime is equal to 0. Okay, so we're gradually making this simpler and simpler here. So let's rewrite this wave vector q in the following way. So let's set little q is equal to little k minus big K. So big K will be chosen such that little q, big K rather, will be chosen such that little k lies in the first Brillouin zone. So big K is a reciprocal lattice vector. Such that little k lies in the first Brillouin zone. Okay, so Q can be any wave vector satisfying our boundary conditions. It need not lie in the primitive cell of the reciprocal lattice, but we're going to shift it back, if you like, into the first Brillouin zone by choosing an appropriate reciprocal lattice vector, big K, such that little k here does indeed lie in the first Brillouin zone. So for a given Q, we have a discrete and finite number of choices of big K that landed back into the first Brillouin zone. Remember, there's only a finite number of vectors little k in the first Brillouin zone as well. So with this simplification, or with this relabeling, the Schrodinger equation becomes the following. Okay, and we're going to do one final index swap. We're going to set k prime to k prime minus big K. So again, big K is a fixed reciprocal lattice vector for our choice of Q, and the sum over here runs over all reciprocal lattice vectors K prime. This again just amounts to a shift in the starting point of this sum. So we have h bar squared over 2m k minus big K squared minus the eigenvalue e times c of k minus k plus our shifted sum this must equal 0. This is a restatement of the Schrodinger equation. It takes this form because the potential is periodic in the lattice, and the wave function is also periodic because of the boundary conditions. So now let's just pause and interpret this equation here. So let's imagine fixing little k, and remember that little k lies in the first Brillouin zone. Okay, let's also fix big K, which is any reciprocal lattice vector, such that the difference of these is equal to our initial wave vector q. Now, the thing to realize here is that for fixed little k and big K, this equation involves all coefficients where all Fourier coefficients C, where the wave vector differs from little k by a reciprocal lattice vector. So here I have C of little k minus big K. Here I have C of little k minus big K prime, and big K prime runs over all reciprocal lattice vectors. Now let's imagine I choose a different wave vector Q. Let's suppose I choose a different wave vector, a different reciprocal lattice vector, big K here. You see that the equation for the same value of little k, but that different value of big K, still involves only coefficients C, where the overall wave vector differs from little k by a reciprocal lattice vector K prime. So only those coefficients that differ from little k by a reciprocal lattice vector are mixed together by this equation. So what that means is that, in fact, we can express then the wave function as a Fourier series with only those coefficients non-zero, as only as a sum over plane waves where the coefficients differing from little k by a reciprocal lattice vector are non-zero, right? This is, we've vastly restricted the set of non-zero coefficients here because the potential is periodic in the reciprocal lattice, all right? So what we can say then, so for each vector little k in the first Brillouin zone, we can write psi of little k is equal to a Fourier expansion over plane waves that differ in their wave vector from little k, this quantum number, by a reciprocal lattice vector big K. And again, we can write down this simplification because it was only these vectors, only these coefficients that were coupled together by the Schrodinger equation. All of the other coefficients can be zero. It's only these coefficients that are in general not zero. So we're free to restrict now the sum in this Fourier expansion over only those wave vectors that differ from little k by a reciprocal lattice vector. So what this means is that we can write the wave function then as e to the I k dot r times the sum on big K, C of little k minus big K times, getting ahead of myself here, e to the I big K dot r. Okay, but this is clearly a function with the periodicity of the lattice. It is built out of plane waves with reciprocal lattice wave vectors. By definition, those have the periodicity of the lattice. So if I write it like this, this function u is the same as this quantity underlined by the square bracket. This very obviously has the periodicity of the lattice. This is indeed of the Bloch form. So we have proved Bloch's theorem in another way just by looking at the Fourier expansion of the Schrodinger equation. So let me emphasize that this works because we've chosen the value of little k to lie in the first Brillouin zone. Remember, the essential step was that it was only the coefficients with wave vectors differing from little k by a reciprocal lattice vector that are coupled together by those equations. That step, that assumption, that simplification is made possible because we chose little k in the first Brillouin zone. Had we not restricted little k to lie in the first Brillouin zone, we would not have been able to make that simplification. We would not have been able to see that only those coefficients are coupled together. Okay, so that's one important point about this derivation. Another point is to realize that actually there's an infinite number of solutions for these coefficients, even for the fixed value of little k. These solutions are indexed by another quantum number, the band index n, which we talked about, or which we mentioned briefly at the beginning of the previous mini lecture. So this is something that we'll come back to again later on in this course.